Okay, welcome to Let's Get to the Marks, going through an A-level chemistry walkthrough about the trends across period two. Don't forget I'm here to help you smash your exam, so do me a favor and hit the like button. It helps with the YouTube algorithm. Right, let's get into this one. The first ionization energies of the elements in period two change as the atomic number increases. Explain the pattern in the first ionization energies of the elements from lithium to neon. And this one's worth 6 marks. I suggest you grab a pen, grab some scrap paper, pause the video, have a go. Then unpause, watch the walkthrough. Anything you didn't get, make a note of. And that's working smart rather than working harder. So just fix up on your mistakes. Let's go. So as we move from lithium to neon across period two, and you can see on the periodic table here, the atomic number is increasing. So what does this mean? This means the number of protons in the nucleus is also increasing. So, for instance, when we went from beryllium to boron, there it went from 4 to 5, or from boron to carbon, it goes 5 to 6. Now, if you have more protons, that means you have a greater attraction between the nucleus and the outer shell electrons. What does that mean? That means that those outer shell electrons are held more tightly to the nucleus. There's no extra shielding as well because electrons are being added to the same shell, as you can see here with boron and carbon. So electrons are pulled closer to the nucleus. Notice I'm using the E minus sign as a shorthand for electrons. Probably best not to in your written answers. Um, all this that we've talked about, the fact there's no extra shielding, the fact the nuclear charge is increasing and the outer electrons are more strongly attracted by electrostatic force of attraction to the nucleus, all of this means the ionization energy, the general trend is an increase in ionization energy from lithium to neon. It requires more energy to remove that electron, to overcome those electrostatic forces of attraction between the nucleus and the outer shell electrons. So this is really, if we answered all of this, we may score 1, 2, possibly 3 marks. Now we need to look at the deviations from the trend. And there's two major deviations going across the period. And the first one happens between group 2 and group 3, and the next one between 5 and 6. And now we're going to talk about the deviation between beryllium and boron, which is the group 2 and 3 deviation. Now, we would expect boron to have a higher first ionization energy for everything we've written in black there above. That's what we would expect. Boron has 5 protons compared to beryllium's 4, so we would therefore expect there to be greater attraction between the nucleus and the outer shell electrons, and there is greater attraction. But when we look a little bit closer, we're going to see something else that actually changes the order of the first ionization energies. So when we look at beryllium, it has a full 2s subshell, and so does boron, but boron has this lonely little electron in a 2p subshell that is slightly further away from the nucleus at a slightly higher energy level than the s subshell, and of course therefore it has a little bit of shielding from the 2s subshell, and that electron is actually easier to remove than breaking into that full subshell in beryllium and removing that electron. So once again, the reason why boron and beryllium don't fit the general trend of an increase in first ionization energies is because the boron electron is being removed from the 2p subshell that is slightly further from the nucleus and at a higher energy level. And that is why it has a lower first ionization energy than beryllium. So now what does this mean for the marks out of 6 for our answer? Well, the bit in black covers the first 1 to 3 marks. Then you've got the 4th and maybe 5th mark for covering one of the deviations. If you want the full 6 marks, you've got to cover the other deviation. And this deviation happens between group 5 and 6. So we also have another deviation in trends between nitrogen and oxygen. And that's 5 and 6 going across the period. We would expect, once again, for all the same reasons we thought boron would have a higher first ionization energy than beryllium, we'd expect oxygen to have a higher first ionization energy. Why? Oxygen has 8 protons compared to nitrogen 7, so we would expect the greater nuclear charge to pull those electrons closer in, stronger attraction between the outer electrons and the nucleus, so we should think that oxygen would have the first the higher first ionization energy. However, because two of oxygen's electrons are paired together in one of the 2p orbitals, this means there's extra spin pair repulsion. And this is what you need to do to get those extra marks. You need to talk about the extra spin pair repulsion found between group 5 and group 6, and this accounts for the trend being bucked and there being a slight dip between 5 and 6, where oxygen's first ionization energy is below. So if we look here at the electronic configuration of nitrogen, it has 7 electrons, so 2 in the 1s, 2 in the 2s subshell, and that leaves 3 electrons left. So it's got 1 electron in each of the 2p orbitals. You can call those x, y, and z, and that means that they're half filled. And this actually is a more stable configuration than, say, oxygen's, where it has 1 in each of the 2p's, but then it has that 1 extra electron which has to pair up, and we get spin pair repulsion in that 2p subshell. In that orbital in the 2p subshell, we get some spin pair repulsion, making that electron more easily to remove because it has some repulsion. There we go. This would get you all 6 marks. You've covered all 3 things. So the way the 6 marks were weighted, we needed general trend, deviation between 2 and 3, and then deviation between group 5 and 6. Hope that helped. You know what I'm going to say. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Make sure you hit the like, people. It massively helps me out.
You're still here? It's over.